This section is about electrolytes and non-electrolytes. When we dissolve substances in water, we get two different responses. This sodium sulfate will dissolve into ions. We'll get 2 sodium ions, and here we've got an S that means solid, and after we dissolve it in water, it's going to be aqueous. We put AQ plus, and then we'll have a sulfate with the 2 minus charge, and it'll also be aqueous. So sodium sulfate dissolves into ions, and it is an electrolyte. This is the formula for sugar, and when it dissolves in water, it becomes aqueous sugar. There are no ions formed. It's just aqueous now. So let's look at a diagram we've got. We can see how this affects the conductivity of electricity. So let me get look at this, and we'll shake some salt. Well, first, before we shake the salt in, let's check the conductivity. See, this is a conductivity meter. It's got a positive over here, an anode over here, and a battery. So if this solution will carry charges, the light bulb will come on. The current will move through the water and then up and through the light bulb. So no conductivity here in pure water. Let's add some salt. Here's our salt. And then let's try the conductivity again. Okay, now the light bulb is lit. And that's because we're getting, and I'm not going to be able to write on that. We're getting the water here, because of the salt, is able to carry the charge from the positive to the negative. Let's see if we do sugar. Let's remove salt. Let's put some sugar in here, and we will find that however much sugar we add, we do not get, the conductivity does not increase. We're not able to get the light bulb to come on. Let's look at what's happening at a microscopic level. So we're going to drop some sodium chloride in here. So here's the sodium chloride. We've got the big sodiums and the little chlorides. And you notice that they're all stuck together when they come out of the salt shaker. Let's see what happens as they hit the water. So as they hit the water, they move independently. So we have negative and positive charges moving in the water, and that's what's going to carry the electric charge. Let's remove the solute, and let's add sucrose, which is sugar, table sugar. And we'll put that in, and if I can get it to stop. We see it's all in one big clump as it comes out of the sugar shaker. But it stays in these large clumps. They don't come apart. We have 3 large sugar molecules, not little pieces that are charged. And these large molecules are not charged. So let's go back to our lecture and fill out our table. Strong electrolytes will conduct current because they do form ions. And examples here, the most common one is sodium chloride, magnesium nitrate is the other one. And third one would be this sodium sulfate that I had in my other example. Non-electrolytes do not carry current. They do not form ions. They stay as molecules. And examples are sugar, glucose, which is a single sugar, and urea. There are lots and lots of examples. Now, you'll notice that I didn't do weak electrolytes. Weak electrolytes are sort of in between. They conduct current weakly, and they dissociate a little bit. They form some ions. And examples here, ammonia is probably the most common. So when potassium perchromate is a strong electrolyte in water, and we use an arrow here to indicate that this reaction goes in one direction. And we denote that we get ions. We expect that for a strong electrolyte. Here we have a weak electrolyte. When we have a weak electrolyte, we draw two arrows. That shows that the reaction is reversible. And in dissolving solid sugar in water, we show one arrow going in the forward direction, but we indicate that it's aqueous. When we're talking about electrolytes, we need to define the word equivalent. An equivalent is the number of charges present per mole. So, how many equivalents are present in 1 mole of sulfate? Well, each sulfate has 2 charges, so we get 1 mole times 2 charges, and that gives us 2 equivalents. 4 moles of chloride, well, we have 4 moles, but each chloride has 1 charge, so we'd have 4 equivalents. 2 moles of iron 3 would give us 2 moles times 3 charges, and that's equal to 6. Does not matter for equivalence whether the charges are positive or negative. It just matters that it's a charge. So let's take a look at this problem. We're going to start with laboratory tests for a patient indicates blood calcium level of 8.8 milliequivalents per liter. How many moles of calcium are in half a liter of blood? So we're going to start with our half liter of blood. And we're going to convert that into an unknown number of milliequivalents, and then we're going to convert it into equivalents, and finally we'll convert it into moles of calcium. Now, this is the first conversion. We can use this statement right here. We know that 8.8 milliequivalents is equal to 1 liter. It's supposed to be an 8. Okay, milliequivalents to equivalents. We know that there are 1,000 milliequivalents in 1 equivalent. That's just what the milli means. This last one, because there are 2 charges here, 1 mole of calcium ions will have 2 equivalents. That's because we've got 2 charges with each calcium ion. We know that calcium has 2 positive charges because it's in the second column of the periodic table. So now we're ready to do our set up our problem. We're going to start with the 5 liters of blood. I'm trying to draw kind of a long line here. Okay, our first conversion will be to get rid of the liters and change it into milliequivalents. Our second conversion will be to get rid of our milliequivalents and get equivalents. And our third will be to get rid of equivalents and end up in moles of calcium. So if we do all the math on this, we will get 0.0022. So that's 0.5 times 8.8 divide by 1,000 and divide by 2. This is the number we get. Let's see what units we end up with. Well, liters canceled here, milliequivalents canceled here, equivalents canceled here, and so we were left with moles of calcium.